Hello, my name is Ning, and I'm a student in the class Center on Cognition, Brain, and Language. Today, I'll present our latest work on the neural representations of unseen contents in the human brain and in deep neural networks. Despite advances in the neuroscience of visual consciousness, we still lack an experimental framework to pinpoint unconscious information processing. We used a within subject high precision fMRI decoding approach to investigate the matter. We recruited 7 participants. Each participant came to the fMRI 6 times, and each time they went through 288 trials of the experiment. This allowed us to perform within subject analysis of both fMRI and behavioral data. We use a behavioral paradigm that masks rapidly presented images embedded in noisy backgrounds. Participants were asked to respond to the categories of their images, such as living versus non-living, and then rate their level of awareness. There were 3 awareness ratings, from no experience to glimpse it to clear images to clear experience. We will focus on the first and the last ratings, unconscious and fully conscious trials. In the bottom left figure, the left half of the volume plot shows the resample behavioral performance, and the right half of the volume plot shows the estimated chance level by permutation. Behaviorally, we found 4 out of 7 participants show no perceptual sensitivity when they reported no experience in these trials. The remaining 3 shown above chance perceptual sensitivity, even though they reported no awareness of the stimuli. We then conducted an RI-based multivariate pattern analysis on the fMRI data. Interestingly, we were able to decode significantly above chance the categories of images from 6 out of 7 subjects in the fusiform and the middle frontal drivers, particularly in those 4 subjects who showed no sensitivity. And additionally, we asked if the multivariate pattern of the image categories generalized from conscious to unconscious trials. We therefore trained a linear classifier on the conscious trials and then tested it on the unconscious trials. And we found that the multivariate patterns generalized in the fusiform lateral occipital cortex and precuneus. We also have some evidence that the patterns could be generalized in the middle and inferior frontal areas as well. We then tried to model the observed phenomenon by having feedforward convolutional neural networks to perform the same task as the human observers. We used different FCNN models performing the perceptual task with different levels of Gaussian noise in the image. Previous study has shown the similarities between the higher order layers and the inferior temporal areas of the human brain in the representational level. We asked whether the hidden layer representations of the FCNN contain information of the image classes, even when the FCNN performance was at the chance level of classifying the images. We stripped the last few fully kinetic layers of the pre-trained CNN model, and then we added 2 newly kinetic layers. We first freeze the convolutional layers and train the newly kinetic added layers to categorize the images used in the fMRI experiment with clear backgrounds. After training, all the model weights were frozen, and then we tested the trained models with images that added various levels of Gaussian noise. In the meantime, the hidden layer of representations of the noise images were used to decode the image categories by a linear classifier. If the model categorized the noise images poorly, such as the AOC score was lower than 0.55, we performed the decoding test. This is due to a computational power limit. In total, we tested more than 800,000 cases. Here are the results. In the figure, we present the performance of the model as a function of the noise level in black, and the performance of the decoding scores from the hidden representations as a function of the noise level in blue. Each row shows a combination of activations functions of the 2 fully kinetic layers, and each column shows a selected preaching CNN backbone. The size of the dots indicates different dropout rates, and the shape of the dots indicates a different size of the hidden layer. In most cases, we observe that there existed information in the hidden layer representations that were not read out by the last layer. Lastly, we focus on those models and noise levels where the FCNN models were at chance in categorizing noisy images. Shown in the figure on the right, we present the performance of the decoding scores from the hidden representations as a function of noise levels, and all the cases here are when the FCNN models categorize the noise images at chance level. The vertical dashed line indicates the median of the noise level. We divided the full spectrum of the noise level into low and high conditions. In more than 12,000 out of these 32,000 cases, the hidden layer representations of the noise images contain enough information for a linear classifier to decode the categories of the images. When the noise level was low, we could decode from more than 75% of the cases. When the noise level was high, we could still manage to decode from almost 29% of the cases. What we want to emphasize in the end is that first, the representation of unconscious contents, even when no perceptual sensitivity, is distributed across the ventral visual pathway and involves fronto-parietal areas in most of the participants. Secondly, similar to the brain, the simulation results indicated that across a wide range of deep neural network configurations, the hidden layer of the neural network was informative of the image categories, even though the network classification accuracy was at chance. These results suggest revision to the global workspace theory account for the shared neural representations between conscious and unconscious state, and the PFC involvement in representing unconscious content. This is the end of the presentation. Thank you for your attention.